This conference will now be recorded.
Very good afternoon, students.
This conference will now be recorded.
Very good afternoon, students. Today we will discuss few questions from JEE Advanced papers on the topic magnetics and electromagnetic induction. So this is chapter 4 and 5, and this is chapter 6. Okay, so let us start our discussions. See, in the first question it is said a steady current flows along an infinitely long hollow cylindrical conductor of radius small r. So the situation is something like this. So this is a hollow conductor, cylindrical hollow conductor like this, and it is actually carrying a current I. Okay, and it has radius r. Okay, radius r, diameter of which way say that is 2r. Anyway, so I'll just redraw the situation. Oh, sorry. So this is a cylindrical conductor, and in fact I would like to give dot 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 both sides because it is infinitely long wire carrying a current I, and it has a radius r. This cylinder is placed coaxially inside an infinite solenoid of radius 2r. So I have another solenoid of radius double of this, okay, 2r. I have this, say this one. This is also infinitely long, infinitely long. The solenoid has n turns are there, and each turn n turn per unit length, and each of them are carrying actually I current again. Consider the point P at a distance r from the common axis. Correct statement is or are. So here you have to find out which one is correct option. So options I'll read. In the region 0 to capital R, that means inside the first conductor, inside the conductor, magnetic field is non-zero. We'll decide, like we'll answer it. First of all, let me read the options. In the region small r is equal to, see this region is in between the cylinder and the solenoid, so somewhere here inside the solenoid, okay, inside the solenoid. Now in the region r to 2r, see r here and 2r here, the magnetic field is tangential to the circle of radius r centered at the axis, centered on the axis, okay, so that we'll find out. And in the region r greater than 0, the magnetic field is non-zero. We'll take up one by one, and then we'll justify whether some statement is correct or wrong. Let me draw the same figure here. Drawing horizontal line is much easier than drawing a vertical line. I don't know, maybe it happens for me. Anyway, So this is having a radius 2r. So this is 2r, say. So this is the solenoid. Okay, this is the solenoid. It has n turns per unit length. Per unit length. All right. Now I'm drawing the cylindrical. See, this is actually going up to infinity. Okay, this also goes up to infinity. And each turn is carrying current I. So if we want somewhere, we want to calculate the total current anyway, it is infinity, doesn't matter. So we'll see inside this solenoid, the conductor of radius r is kept like this. Okay, it is kept like this coaxially. Coaxially they are kept like this. Okay, both are infinity, actually both are infinity. So this one is carrying current I, and this one is also carrying current I1. Sorry, I at each turn. So now the question is, see, if I just take the region 0 to R, this region actually inside the conductor, inside the hollow conductor, hollow, LLOW, hollow conductor. So inside the hollow conductor there will be no charge, right? And first of all, you can apply By-Savart law, sorry, Ampere circuital law to calculate magnetic field due to a wire. If it is internal point and this is hollow, then we have seen that magnetic field is 0. So look inside this, due to conductor, magnetic field will be 0. But what about solenoid? This the whole region is inside the solenoid. So this region is inside the solenoid also. Inside the solenoid. See, magnetic field due to the conductor will be 0. But what about solenoid? The magnetic field generally be here inside the conductor, right? Outside the conductor, sorry, outside the solenoid, there will be no magnetic field. So therefore, in this region, magnetic field will be non-zero, which is correct. See, this option is correct. Magnetic field will be non-zero. That is due to, this is due to the solenoid. Due to the solenoid. Right? This is due to the solenoid. So in the region R, less than R and 2R, that means that this is said the magnetic field is along common axis, along the common axis. See, it is said the region is this R to 2R, this region, that means inside the solenoid. Inside the solenoid, magnetic field, how the magnetic field will be, whether it will be along the common axis direction, it is not true, because for infinite magnetic field, so sorry, infinite current can conductor, if the current is flowing through this way, magnetic field will be inside into the plane of the paper. Here it will be out of the plane of the paper, right? So therefore the magnetic field is not along the axis, because net direction will be something else. So that's why it is not true. Acha. Then third option is R to 2R region. The magnetic field is tangential to the circle of radius r, and centered in the. So this also may not be true, because as I said, see, in this region magnetic field cannot be tangential. always, because see magnetic field due to solenoid is axial and due to the wire is actually like that. Wire is tangential to the circle. Okay, so that is also not true, because we have to see the combined effect of both the conductor and the solenoid. What about the last option in the region r greater than 0? See, r greater than 2r, that means here somewhere, here it is, here some distance r, so it is here the distance, that means outside the solenoid. When outside the solenoid, whether there will be magnetic field non-zero, whether magnetic field will be non-zero outside the solenoid? No, because this infinite conductor can create magnetic field which can be there. Okay, which can be there even up beyond the solenoid. Okay, so in this region also magnetic field will be non-zero, and inside this also will be non-zero. These are two correct options. Okay, these are two correct options. I have discussed why and which one is correct. We'll go to the next problem. This is very interesting problem. Look, this question is saying that this is also from JEE Advanced 2013. So question says that a particle of mass capital M and positive charge capital Q moving with constant velocity u1 is equal to 4 I ms, sorry, 4 I cap uh, meter per second enters enters the region of uniform magnetic field normal to the xy plane, normal to the xy plane, the region of uniform magnetic field normal to the xy plane. So you can see there is xy plane. This one, say this is x, this is y, and the magnetic field is perpendicular to the direction, or perpendicular to the xy plane, normal to the xy plane. Magnetic field is uniform and static magnetic field, normal to xy plane. The region of magnetic field extends, the region of magnetic field extends from 0 x is equal to 0 to x is equal to L for all values of y. After passing through this region, the particle emerges on the other side after 10 milliseconds with velocity this. The correct statements is or are: the direction of the magnetic field is minus z, and the direction of the magnetic field is plus z direction. Magnitude of the magnetic field is 50 pi m by 3q units, and magnitude of the magnetic field is 100 pi m by 3q units. Okay, so magnetic field is here. So this is the question. Look here, one thing we have to understand. See, we can intuitively draw this figure. See, in the xy plane there is a region where there is uniform magnetic field, and magnetic field is perpendicular to the xy plane, perpendicular to the xy plane. And see, this is the velocity with which it was started. It started moving like this, and then finally, since there is magnetic field perpendicular to the xy plane, so it will undergo a circular motion. Okay, the charged particle will undergo a circular motion, and it will stay inside the magnetic field, okay, till 10 millisecond, and within that it will move up to this point, okay, this point in the magnetic field. and when it leaves the magnetic field, it has velocity u2 is equal to this. This is the velocity it has got, whole 2 into, or I can write this u2 is equal to 2 root 3 I cap plus 2j cap. Okay, so this is the final velocity after leaving. That means, you know, that this velocity is making an angle with x-axis. How do you find out? Tan theta is equal to 2 by 2 root 3. So this is 1 by root 3. This is theta is equal to 1 by, okay, tan theta is equal to 1 by root 3. So which implies theta is equal to tan inverse 1 by root 3, which is actually 30. So 30 degree is the angle which the velocity vector is making with the horizontal. So by symmetry we can see this angle is also 30 degree. So if we get that, then you look here, this is the arc length. If we require, we will be able to find out what is the arc length. The question is the magnetic field is along the z direction. Yes, so magnetic field is actually along the negative z direction. This is true. This is true. Otherwise, this velocity would not have happened. Okay, because you know v cross b is equal to the force, right? The force, and when you multiply these two, you had this velocity already. I cap was there. Okay, I cap was there. Now velocity is perpendicular to, see, I can write it here, vx. It is given, it is perpendicular to the xy plane. That means it is obviously k cap. Okay, so look here, ui. So we can actually get vi cap cos plus vy j cap cross k. So this is, look, v I cross k, I cross is minus j, right? Minus j, so vx minus j, and this is again k cap. So vy, jk means I, so this is vyi. Okay, if you compare this two with this velocity, sorry, this is actually force. Okay, we will not be able to compare with this now anyway. So this is how intuitively you understand that this magnetic field is along negative z direction. Okay, now it is not true positive z direction, that is true. Now we have to find out what is the magnitude of the magnetic field. What is the magnitude of the magnetic field? How to find out that? To find out the magnitude of the magnetic field, see, look, I'll just refer to this figure. So theta, angle theta is here actually pi by 6, and we know angle theta is equal to arc by radius, arc by radius. Okay, so we have to find out what is the arc length. Here arc length is speed is given, right? Speed is given, into time is also given, divided by radius. Radius, you know, m square by r is equal to qvb. Okay, so v goes from here. We have to find out what is the radius. R is actually, r is as mv by qb, mv by qb. So this we can actually apply here, mv by qb. This is the radius of the arc. What is the speed? Speed was given, right? Speed is given, this one. So angle is actually pi by 6 here. Speed into time, qb by mv. Okay, qb by mv. What is the speed? Speed can be taken as the initial speed 4 into t is the 10 millisecond, 10 to the power minus 3. Q, let it be, and B is there. Okay, so we have to actually find out the magnitude of the magnetic field. That's it. We have to do. This is speed into time. Time is 10 millisecond anyway. This is mv by qb. So qb goes up. mv, m is this, and okay, so we will get it here. Let us not write the v itself here. Speed, let us say v, and see here it is actually mv by qb, q and b, mv. So this b goes off. So here we have to actually find out b, right? So b will be is equal to pi m by 6 into q into 10 to the power minus 3. Okay, 1 millisecond. So this t is the millisecond I have used here, and vb I have just strike them out. So this will be 1000 pi m divided by 6 into q, right? So we need to see magnitude of the, so this is 5. Let me check one thing. 4, okay, 0 to L. All right. So this is actually 500. It is coming 3q. Somewhere some 10. Okay, this 10 millisecond. Okay, this was 10 millisecond, not only millisecond, 10 millisecond. So 10 is here, 10 millisecond. Okay, 110 will be, well, okay, so this is 50 pi m by 3q. So this is the strength of the magnetic field. So we have seen the first option. This is the magnetic field in the z direction, minus z direction, and this is the strength of the magnetic field. This is not true again. So this is how we have to solve this problem. Now we'll move on to the next problem. Maybe let us do this first. Oh. This is from induction part. So we have already solved two problems from magnetics. Let us solve this problem from induction today. Okay, so this question says a rigid wire loop of square, a rigid wire loop of square shape having side of length capital L and resistance capital R is moving along x axis with a constant velocity v in the plane of the paper. At t is equal to 0, you can see here this is actually x direction and this is actually position. So at t is equal to 0, right edge of the loop enters into a region of length 3L. At t is equal to 0, the right edge of the loop enters a region of length 3L. Okay, that means actually enters a region 3L where there is a uniform magnetic field B not into the plane of the paper as shown in the figure. So magnetic field is into the plane of the paper and it is a constant value, that is B0. For sufficiently large value of large V naught, the loop eventually crosses the region at x b, the location of the right edge of the loop, Vx f of x, then the current. So this is Ix means current, this is Fx means force, represent the velocity of the loop, current in the loop. So Vx is velocity, I current, and F is the force on the loop respectively. So you have to actually find out which one of the following plots is correct, ignoring gravity. Okay, so we have to choose the graph. So here actually this problem is based on the motional EMF. The concept one has to deal with are the Lenz's law of induction, right, and the magnetic force on a current carrying conductor. Here you need to find out the direction of the induced current and the direction of the magnetic force, the loop, and then one can easily answer the question. Okay, so what you have to find out? You have to find out the direction of the induced current and the force, direction of the force on the loop. Then you can be able to find out the answer. So this is a problem of motional EMF, as I said, and you can solve it by considering the Lenge's law and magnetic force. So look, what is the direction of the current when the loop is in between 3L and 4L? We have to find out that. Just a minute. We will actually analyze each and every point and try to answer. It is related to motional EMF. So the loop is actually in the plane of the paper. Plane of the paper. Velocity is along the plane of the paper, like in the plane of the paper, but magnetic field is in the direction perpendicular to the plane of the paper. So you look here, first of all, we have to find out how current is getting induced at different region. See, when I will just try to see, suppose this is the loop, it just enters here when x is equal to 0. X is equal to 0, and in this region, when this particular structure is there in this region, what is the current? Magnitude of the current, whether here induced current when it moves from this place to this, when just enters into this, see when the magnetic, so when this structure enters into this, then there is a change in the flask, right? There is a change in the flask. Change in the flask, there is a change in the flask. So v is actually a constant velocity, so there is, see, motional EMF is bvl. L is the length of this loop. So b is constant magnetic field or uniform magnetic field. V is uniform, so these are actually constant. Only point is that length, when length changes, then length means not this length again, the length of this loop, length of the loop is changes. Then see, we know the flask is actually b into a, so if b is changed, then magnetic field, like flux changes. When area is changed, then also flux change will happen. So that's how, if the length varies, then magnetic field will, sorry, magnetic flux change will be there. So let us see how does the magnitude of the induced current change in different regions. First of all, the magnitude of the current remains constant for all the regions, but direction of the current changes. See, if we look here, when just enters, there will be induction, okay, there will be induction. But when it is oil inside here, since this bv doesn't change and L also is not changing, so oil inside this region, induced magnetic field will be actually, sorry, induced EMF will be 0. At this region, induced EMF will be 0, L to 2L. In this region, it is 0. Even in fact, when it L to up to 3L, L to 3L, in this region, magnetic flux will be 0 actually. Induced current, so induced current induced current is maximum at x is equal to 0 because just it enters x is equal to 0. Then it decreases as the loop goes inside because there is no change in the magnetic flux for that when it goes into this region. Okay, in the region 0 to L, because after that it will be covered. Okay, 0 to L, in this region, see, as it enters it was increasing, magnetic field flux was increasing. Then as it starts entering and entering, when the length becomes L, okay, the whole loop enters into this, then whole thing is enters into this, then there will be no change in the flux. Okay, so 0 to L, it is actually at x is equal to 0, it is increasing, it will be decreasing, so it will be decreasing when L goes from 0 to L. Okay, now when it is L to 3L, in this region the induced current will be actually 0 because at this in between this region there is no change in the flux. So we have what we have current and voltages and forces. These are the things we have: current, voltages, and force. So you look this guy. So when the magnetic flux just x equal to 0, magnetic flux was maximum, then it start becoming 0, and at L to 3L it is actually 0, L to 3L 0. Then again when it is going away from the region, so there will be, so when it is 3L to 4L, 3L to 4L, in this region what happens? In this region again, some value of magnetic, see, when it is actually just going out of this region 2L 3L, like when it goes from 3L to 4L, just when it is going out there will be maximum flux change. But when it is at 3L to 4L, in this region, there will be no change in the flux, so there will be decrease in the current. Okay, decrease in current, right? I'll summarize what I have said. See, when there is a loop, square loop like this, and magnetic fields are there through this. Now if the magnetic field, say BVL is emotional EMF, any one of these three parameters has to change so that there will be induction. Otherwise there will be no induced EMF and no current as well. So we'll divide into region 0 to L, L to 3L, and 3L to 4L. So in between 0 to L it was maximum, then it falls down, it is fine. So 0 to L to 3L it will be 0, again it was maximum, there from there it will be falling off. So this seems to be correct. Let us see this one. So this is going negative direction. So Regarding current, you look, this is actually going out, right? Between 3L to 4L, it is flux is decreasing. Here it was increasing. It was increasing. Flux was increasing. That's why it is maximum to 0. So the current, this one is fine here. Here also it is fine. But you look here, it is actually going out. So the current is going to be 0. Flux is actually decreasing. So it will be actually in the negative direction. So this option will be correct option here. Okay. The next option is see if the current is becoming this, then how it will vary with voltage? How will be the voltage? So this has a slope anyway. It has some slope. So it is voltage I into R. I into R, right? I into R. So it looks like this. And in between L to 3L, there will be constant voltage. There will be no zero voltage. There will be constant voltage. That is also true. And thereafter 3 to 4L EMF will be decreasing. So this is also true. So we see C and D are true. Okay. And what about magnetic force? Magnetic force IL cross B. IL cross B. The force is IL cross B, right? IL cross B. So we need to see whether for the force 0 to L, during this time it has to be actually positive. Then force may be 0, but why it should be 0? B is there, I is there. For force, so this is not true. Therefore, we had these two options, C and D. Okay. All right. So we need to find out what we need to find out. We need to find out current, how current is generated in this region, how EMF is varying in this region. Okay. So when it enters, the flux grows in. Okay, flux grows, and it is maximum at x is equal to 0. When it goes x is equal to L, then the uniform flux, see, flux will be uniform, there will be no change. And if uniform flux is there, there is no induction, so current will fall after this. So it was earlier positive and it will be negative here, 3L to 4L. Okay, so this is how we have solved it. We'll stop it here for today. Next day, we'll take up questions from induction and other part. So thank you for your patience. Bye for today.